Okay, thanks for having me here. And my name is Dongmin Shin, and I'm an AI ops engineer at Reed in South Korea. Today, I'm going to introduce state-of-the-art model in knowledge tracing, which is called SAINT+. Actually, SAINT+ is a model that performs knowledge tracing, which is called KT. And KT is, for many years, it becomes the foundation of intelligent tutoring system, which is called ITS. And ITS is getting more spotlighted in the period of post-COVID-19 because of an online education is emphasized. So KT is the research area to model a student's knowledge states. And many preliminary researches show that KT allows us to diagnose students' learning states and use it for learning content recommendations. So therefore, it is important to create a high-performance KT model to achieve a better quality ITS. So let's look at some brief history of knowledge tracing. BKT is the first model of knowledge tracing, and the authors of BKT defined student knowledge states as a set of binary variables, and this state is updated by students' learning activities through hidden market model. So the target task of this BKT model is predicting students' knowledge state directly. But after that, collaborative filtering-based KT model is appeared. And in CF, students in exercise are modeled as on low-rank matrices, respectively. And the model predicts the correctness of an exercise for given students, and the multiplication of two matrices is the correctness probability of given exercise for given student. And from CF-based KT, the student's knowledge state is viewed as latent in the vector of student matrix, and the state is learned indirectly from correctness prediction. And after that, the first DL-based KT model is appeared in 2015, which is called DKT, Deep Knowledge Tracing. DKT use recurrent neural network, and DKT models students' evolving knowledge state through this network, and RNN compresses their past, RNN have an ability to compress their past learning activities in their network. And like CF, DL-based KT models learn student knowledge indirectly while performing correctness prediction. Maybe the learning, the student's knowledge states can be learned in latent in the network. And the later models have been trying to improve the performance correctness prediction in the same scheme. So, for example, DKVMN is used memory network for predict correctness for of the students, and then SAKT used transformer encoder, and the SAINT used transformer for the correctness prediction. Then I'm going to explain some researches related to the model architecture of SAINT+. This slide shows that the comparison between transformer and SAINT. I'm not going to explain detailed model architecture of transformer or SAINT, but I'm going to explain some differences between them. Transformer is originally designed to perform machine translation task. For example, English-French translation. In this case, English text is fed into the encoder part as source token at the left part of this. And then French text is fed to decoder part as a target token. And transformer shows superior performance in machine translation tasks compared to previous models. SAINT is a model that transforms transformer to fit KT. So for the Saint separates the user interaction data, which is consists of exercise ID and topic that exercise belongs to or correctness kind of things, separates in two parts, exercise related data and response related data. The examples for exercise related data can be exercise ID and maybe part of things. And and that kind of data is fed to encoder parts. And then the response data, like correctness kind of things, are fed into decoder parts of the model. Okay. Due to this setting up this Saint, the model the architecture of model is changed from transformer. The subsequent mask, which is represented as upper triangular mask on the left encoder part, is introduced to Saint prevent using future exercise information for their predictions. And there are some case studies introducing time-related features to knowledge tracing. And many of researchers shows that the performance of the model is getting better when introducing time-related features. For example, elapsed time or lag time, etc. And there are some studies, which is the study of the second bullet point, try to find some pedagogical implications of the model performance. And others claim that there's a relationship between lag time and the student forgetting behavior for that. And based on this related works, I propose Saint Plus. And Saint Plus is a model that integrates time-related features into Saint. Top of Saint, I added the sum of two temporal feature embeddings to decoder. The one is elapsed time embedding as continuous fashion, and the other is lag time embedding as categorical fashion. And this figure shows that how I define the elapsed time and lag time for the data in the data set. Elapsed time is the time gap between when the user received the question and when they answered the question. So for example, in this figure, T2 minus T1 can be elapsed time, and T4 minus T3 also can be elapsed time. And it's just simply the user's exercise solving time. And the lag time is a time difference between when the next exercise is received and when the previous exercise is solved. So in this figure, T3 minus T2 and T5 minus T4 can be interpreted as a lag time. And in this period, students can study other contents such as commentary of the exercise or some lectures related to the exercise, or take a break or stop learning at all. So I use two different strategies for temporal feature embeddings. First one is continuous embedding. Continuous embedding is just the product of single learnable vector, which is represented as WT, and scalar value T. T is the value divided by the maximum value, which I set it as 300 seconds for elapsed time and lag time. And then for categorical embeddings, I discretize value by some rules and creating different learnable vectors for each discretized values. I use different discretizing rule for elapsed time and lag time. So elapsed time is discretized by each seconds up to 300 seconds. So theirs will be 302 unique categories for this, and include one category for over 300 seconds. And then lag time is discretized as integer minutes as 1, 2, 3, 4, 5, and 10, 20, and etc., and up to 1,440, and there will be 150 unique categories for this, include one category for over the maximum value. And actually, these kind of rules were determined through feature engineering based on the performance of the model. And then let's look at the experiment setup. Before we move on to the experiments, I'm going to introduce the data set I used. The data set I used in the experiment is EdNet dataset. It is the largest public education data, and I used EdNet KT1 from it. And EdNet KT1 contains about 16 million interactions collected from the app that used for studying English test prep, which is called TOEIC. And this interactions is from 144K questions and 680K users. So it's quite a lot, quite a big data sets. And then I select test data set from this EdNet KT1. The test data set I used is an interactions from most recent 10K students. And then I randomly choose 80% of the remaining interactions as a training data set. And then remaining interactions, I use remaining data set as a validation set for the experiments. And this is the hyperparameter settings for the same test. I used item optimizer for the model, and then I used four layers for the same models, and then the model dimension is 512, and I trained this model by batch size at 64. Okay, this is the main result of the table. Compared to other benchmark models like DKT or DKBMN or SAKT, same class showed the best performance according to the accuracy and AUC for this. And to analyze more deeply for the result I get, I did some ablation tests in 3 ways. The first, we did some to find a contribution of each temporal feature. I made 2 variants of same plus. First one is use elapsed time only models, and then the second one is lag time only models for the 2 variants. And then I get when using single temporal feature, the lag time added model shows a greater performance increment compared to the elapsed time model, but using both features show the best performance. And then we changed integration position of temporal features. Maybe temporal features are like elapsed time or lag time corresponds to student response. So it is really natural to add these features to the decoder part, but it can be added encoder also, because model architecture not really restricted to add data in some component to the components. So we just make some variants of this. We made 2 variants of the model. First one is use embed the sum of embeds to the encoder one, and then we just use this the embeddings to encoder and decoder compoundedly. So, but the decoder only model shows the best performance of the ablation tests. And then the last one, this is the embedding strategy for the temporal features. And I made some all combinations of embedding strategies on elapsed time and lag times. So, and we get the best performance when we use elapsed time as continuous fashion and lag time as a categorical fashion. And this is the last slide of my presentation. And there will be some future works for move forward after the Saint Plus. In Saint Plus, I just use some exercise solving data, and I'll find some methods to integrate other learning activities like watching lectures or commentaries for knowledge tracing models. And then also exploring some advanced DL architectures, maybe more performant models than transformer, maybe. And also, Saint Plus is already started to use in our product, which is called Santa. And maybe maybe we can make another research for about the user behavior when using KD models. And that's it. Is there any questions or for my presentation?
Thanks, Dongmin. Great presentation. We do have a question already popped up on the Q&A, and it's from Clara. Clara, did you want to unmute your mic and ask your question?
Yeah, I was just wondering, first of all, great talk, and thanks for the great model, great research. What, in your opinion or findings, are advantages or disadvantages of using continuous versus categorical embeddings, besides maybe just showing that one has better prediction performance? Are there any hidden assumptions or maybe other performance indications that are advantages of one over the other?
Okay, thank you. First of all, I just focus on how to improve the model performance of the, how to increase my model performance. So I just think a lot of methods to embedding strategies, not just continuous or categorical fashions. But after I EDA my like EdNet KD1 datasets, then I found some behaviors that I find some like insights from that dataset for elapsed time distribution. When I see the elapsed time distribution, there's a lot of students solve exercise in 1 or 2 seconds. There's a lot of portion in that part. So I think I assume that maybe this kind of data set can be interpreted as guessing when user solve the exercise. And then I move on to the lag time distribution, and I find some very long periods of there's a student who like long period of times to solve the exercise data. So maybe that kind of things can be interpreted as like take a break, or like maybe they need maybe they just stop to use a app. So that kind of behavior can, I think that kind of behavior is much more appropriate to interpreted as categorical features. So I made the kind of the discretizing rules to integrate the kind of meaning that I found to make when I made the discretizing rules. I'm sorry.
All right, Clara, I hope that answered your question. We have another question for you, Dongmin. This is from Zach. Zach, do you want to unmute your mic and ask your question?
Sure, thank you. I remember when the READ challenge was released, and a couple students of mine gave the challenge a shot using classical Bayesian knowledge tracing approaches, and then another one tried a DKT approach, and they found out for this data set, the BKT approach was a lot less performant than DKT than most other data sets like assessments and cognitive tutor and these kind of other public response data data sets. One of the hypotheses from that was that BKT relies much more heavily on very precisely specified skill taxonomies, right? And the association of skills to items. And in this data set, at least in the competition, they weren't called skills, right? They were called tags,
Yes.
Which to us signified that perhaps that meant it wasn't that same kind of very high quality, cognitive task oriented taxonomies and mapping. So could you add more information to those tags that were used for you in this data set? And were they skills, and what was the quality of that tagging? Thanks.
No. Okay. First of all, yes. The EdNet data set is not really focused on the skills, and we just released this data set as just our app usage data. So maybe we just there's only data that we just tag some questions, which is like content for this that data. That is just all we got for this data set. And then this data is handcrafted by some content like experts, which is who is make toy question maker maybe. And then maybe we can just release some information about the tag for the next version of EdNet dataset. Yeah.
Great.
There's two questions from Felix. Felix, did you want to unmute your mic and ask your questions?
Thank you very much. Here the time is a categorical variable you used as a continuous data type as well. So is there a benefit for categorizing time as a categorical type?
Okay. When we use continuous like embeddings, then we just only got just one single learnable vectors. But if we use categorical embeddings, then we have like 100 or some hundreds of learnable vectors. So maybe if the data is enoughly large, then network can learn more specific information from the data set. So it is, I think that it is more powerful to have some rooms for to the network for using by using categorical features, because they have a lot of learnable vectors maybe.
Thank you very much. My next question is, are there any similarities between the validation dataset and test dataset? Because you said that the test dataset is around 10K and validation is 20%, and the train dataset is 80%. So is there a difference for validating the model and testing the final model?
Okay, there's first of some before we started the experiments, this data set is collects the period of collecting data is like 1.5 years at the on the app. So there's a lot of change between there's a lot of change in that period. So we want to make sure that the recent and we have we have some requirements that we have to predict more accurate to the recent users for the deploying the app usage. So we make it harder to and much make more relevant to the current stage of the app. So we just pick test set first, and then I just and then yeah, we make some validation set too. And after the experiments, there's no like difference between the order of model rank or something, but the size of the test data set is larger than validation set. So the accuracy or AUC metrics goes up when we test the sets, and there's no difference between the order of validation and test.
Thank you.
We have time for one last question. Irfan has a question. Irfan, did you want to unmute your mic and ask your question?
Sure, can you hear me?
Yep, we can hear you.
Yes.
Awesome, thank you. Great presentation. I had a question about the embeddings and what's the intuition behind creating embeddings for responses and correctness, and as well as for the temporal features.
Okay. Actually, this part is like I try to just think about how to improve the KT model performance, because if we get the better KT models, then we have a better quality app for our company. So I just tried a lot of things to do how to handcraft these features, and so maybe there's I think there's not much insight-driven like feature engineering. I just want to make this feature to improve my performance, model performance.
Awesome. Thank you for answering. Thank you.